Caterpillar builds the highest quality possible into their products. This is especially critical with engine parts where competition is intense. We can only overcome this competition through a good working knowledge of our parts product. We're going to concentrate on the function, design requirements, and features of Caterpillar pistons, rings, and liners. Since pistons, rings, and liners work closely together as a team, they are usually discussed together. Let's start by looking at the Caterpillar piston. The piston serves as a plunger to compress air within the cylinder. When fuel is injected into the cylinder, the force is transferred by the piston to the connecting rod and then to the crankshaft. In this process, reciprocating motion is changed to rotary motion. Let's now discuss the various areas of a piston and their function. Crown. The crown is the top surface of the piston where combustion takes place. Note the crater shape of the crown, which allows the injected fuel to spread out and burn more evenly than if the top were flat. This crater is present on all direct injection, DI, pistons. Some pistons utilize a heat plug. This will be explained later in more depth. The plug spreads the heat from the combustion chamber and dissipates it through the underside of the crown, where it is sprayed with oil for cooling. Valve cutouts. These provide close clearance for the valves when the piston is at top dead center and allows the engine to be designed for higher compression. Topland. This area between crown and rings. Piston skirt. The area below the bottom ring groove. The skirt prevents the piston from cocking in the cylinder by spreading thrust loads evenly against the liner walls. The skirt also provides additional piston surface area for heat transfer. Pin bore. This is located in the piston skirt and holds the piston pin. Retainer. The retainer is inserted in the pin bore to hold the piston pin in place. Pin boss. The pin boss is the area around the pin bore on the inside of the piston. It supports the pin and absorbs stresses generated as the piston moves up and down. Piston pin. This is the link between connecting rod and piston. Now that we've designated the various areas of a piston, let's review them. There are four major design requirements for a Caterpillar piston. 1. It must be able to withstand high temperatures. 2. It must be strong enough to absorb loads in excess of 15 tons which are created during firing. 3. It must be lightweight, as a heavy piston robs the engine of useful horsepower. Years ago, diesel pistons were large and heavy with many rings. However, the weight tolerance of the pistons and the number of rings caused increased fuel consumption. 4. Its design must match with that of the cylinder wall. Let's now turn our attention to how Caterpillar meets these design requirements and the related features and benefits of our pistons. Cat pistons are made of a low silicon, high alloy aluminum which transfers heat well, is strong and lightweight. We do not use recycled aluminum to make our pistons because we cannot get the purity and quality we demand. Many will-fit competitive pistons use recycled aluminum. All pre-combustion PC pistons have a stainless steel heat plug. Stainless steel resists the high pressure and the heat of injection better than aluminum. It minimizes hot blast erosion, which is caused by excessive heat buildup on the crown. Caterpillar engineers insist on bolt-in heat plugs rather than the cast-in plugs often used by competitors. Cast-in plugs may not always bond securely to the crown because of the complexity of the castings. Additionally, even sound bonds may crack because the aluminum alloy and cast iron expand at different rates when heated. In heavy-duty pistons, which are under extremely high loads, Caterpillar rounds off the sharp corners of the valve cutouts to prevent metal fragments from breaking off and scoring the cylinder walls. Once cylinder walls are scored, we lose the ability to control oil flow. It is a more expensive method of manufacture, but we feel it is important. To prevent cracking of the pin bore, a hard metal roller is passed several times over the core to work harden the aluminum in a process called roll burnishing. The pin bores also have a machined side relief. This pin bore side relief allows the piston pin to flex from a round to an oval shape during direction changes. The piston pin is made from a high-grade hardened steel alloy to resist deflection and breakage. It is also hollow, which allows us to reduce weight and increase fuel economy. Obviously, a piston needs the greatest strength at stress points. Our piston is thicker at the top and in the pin bore area, while the skirt area is thin to save weight. The heavier piston top expands more when heated, which means that thermal expansion will take place unevenly. To adjust for this, Caterpillar pistons are elliptical. The pistons are ground in the shape of an oval with the narrowest dimension through the pin bore. On the left is a picture of a cold elliptical piston. When heated and loaded, on the right, the piston becomes almost cylindrical. Being too oval results in too great a clearance between the piston and cylinder wall. The pressure on the rings will increase, possibly damaging them. Combustion gas will flow past the rings and the efficiency of the engine will be impaired. Without this oval property, the piston can seize due to heat buildup. Additionally, Caterpillar pistons have a tapered top and bottom, which provides a round contact area with the cylinder wall. Without this taper, the piston may seize due to overheating. Too much taper gives too small a contact area against the cylinder wall, resulting in excessive contact pressure and rapid wear. Let's now turn our attention to piston rings and the cast-in ring band. If we could look through an engine and see how rings press against the cylinder wall, this is what we would see. The top two are compression rings. As the name implies, they prevent combustion gases from leaking into the cylinder. The bottom oil ring prevents oil from passing above the piston. All Cat heavy-duty pistons employ 3 piston rings except the 3200 series naturally aspirated, which have only 2 to reduce friction. Compression rings are made from chrome-plated high-strength ductile iron. They are made with a large free gap that, when compressed in the cylinder, is nearly closed. The inherent tension in the ring holds it against the cylinder wall to act as a seal. In addition, the force of the combustion gases pushes the compression rings down in the grooves and out against the cylinder wall to make a tighter seal. Because of this design, we obtain the greatest sealing force when the gas pressure is greatest, during the power stroke. This flexing and sealing of rings results in a high wear situation for both the rings and the grooves in which they sit. For this reason, the face of the compression ring is chrome-plated and polished to a smooth finish. Rings used in hot applications are coated with molybdenum, which has lubricating properties of its own to minimize scuffing. On most Caterpillar 3-ring pistons, both the top and the intermediate compression rings lie in a cast iron band which provides greater wear resistance than the aluminum piston. This feature extends the period between overhauls. Without the cast-in iron band, piston life is drastically reduced. As the uppermost ring wears, the intermediate ring is required to perform an increasing amount of the sealing. Were it not surrounded by cast iron, this intermediate ring would soon wear out its seat, causing excessive blow-by, necessitating an overhaul. Many competitors seat the intermediate ring in the aluminum piston body itself. Once the aluminum is worn out, a whole new set of pistons would have to be bought instead of just replacing the rings as you normally would with Caterpillar pistons. The cast iron band consists of a special type of high-nickel cast iron which is very wear-resistant. During combustion, a certain amount of gases will escape past the top ring. To reduce pressure on the second ring and therefore reduce blow-by, you will find a C or J groove between the top 2 compression rings on most Cat pistons. This groove reduces the pressure by increasing the space that these gases have to expand. Let's now look at some compression ring designs. On the left is a square-faced ring, while the other is a barrel-faced ring. The barrel-faced ring is an improvement over the square-faced ring because it has a more predictable line of contact with the cylinder wall and quicker break-in periods. It is almost impossible to make a square-faced ring perfectly square. If the ring isn't square, the line of contact will vary around the ring. The thin contact area of the barrel-faced ring reduces friction and tends to ride over the film of oil on the liner wall rather than scraping it as a square-faced ring has a tendency to do. A third type of compression ring design has a tapered face. The taper provides line contact with the cylinder wall, similar to the barrel-faced ring. This ring does a better job of putting an oil film on the wall, and it only seals against the wall when there is high-pressure combustion gas to hold it down. Still another type of compression ring is the twist ring. This ring has a tapered face like the ring you have just seen, but it also has a groove machined into the inside upper edge. This groove allows the ring to flex and seal against the cylinder wall even when there is no gas pressure present. This eliminates the condition called slobber, where oil comes up past the rings under low load conditions. Since barrel-faced rings are most adept at sealing under compression loads, they are most commonly used in the top ring groove. The intermediate compression ring must perform both sealing and oil control functions. Therefore, tapered or twist rings are found here. The oil control ring utilizes a double rail design. As shown, the double rail ring scrapes off excess oil in both directions. It leaves enough oil to lubricate the compression rings while preventing unwanted oil from reaching the combustion chamber. Most oil control rings use a tension spring to maintain proper contact with the liner. The spring tension can be changed to vary the amount of oil scraped off. Spring-loaded rings do a superior job, and nearly all Caterpillar engines utilize this design. Pistons and piston rings undergo a rigorous series of tests. Piston ring thickness, height, width, and profile are closely monitored. The witness lap, a band which is lapped onto the face of the ring, is checked carefully. This witness lap expedites break-in of the ring, and quality control inspects these rings to assure that the band extends a complete 360 degrees. Otherwise, blow-by and oil control problems might occur where the ring had not been lapped. Witness laps are exclusively offered by Caterpillar. This is another example of the efforts we take to ensure your customers receive a quality product. The Keystone Profile found on our heavy-duty rings is another dimension which is carefully controlled. The purpose of the Keystone Profile is to keep rings from sticking because of the buildup of carbon particles in the ring groove. Caterpillar engineers feel this profile is so important that the angle tolerance is held to 1/10 of 1 degree angle. It's doubtful if a non-genuine ring is controlled with such care. Metallurgical evaluations are also performed on rings and pistons. The uniformity of the chrome plating on rings, the integrity of the bond between the aluminum piston and the cast iron band, and the general microstructure of the metal are only 3 of the quality control checks made on our suppliers. Our last topic is cylinder liners. Cylinder liners function as the mating surface for the piston rings, except in the 3200 and the 1.1-liter family of engines, which have no liners. Cat liners are designed to withstand high shock loads from combustion. Other design criteria are wear resistance, heat transferability, and corrosion resistance. Unlike pistons and rings, liners are manufactured by Caterpillar. Rough liner castings of alloyed cast iron are shipped to Mossville from our Mapleton foundry. The initial machining operations rough cut the flanges, outside diameter and inside diameter, while final machining shapes these dimensions to close tolerances. The size and straightness of the center bore is especially critical to prevent piston seizure. The entire inside diameter is then hardened by induction heat treating prior to finish honing. Many competitors do not heat treat their liners. As a result, they may not have a high degree of reusability and may often have to be replaced with the rings and/or piston. In fact, Cummins only services these components as a cylinder kit. Caterpillar liners are designed to live through at least 2 sets of rings. After heat treatment, liners are honed. This results in a crosshatch pattern which aids in oil retention. Since our liners are heat treated prior to honing, this crosshatching will be present for millions of cycles, improving reusability. The last step in manufacturing our liners is the process of roll burnishing. This cold working hardens the flange area to increase both its strength and fatigue life. All Caterpillar liners are roll burnished. Caterpillar pistons, rings, and liners are among the most often copied components offered by our parts competitors. Firms like Imperial Cleveite, JP Industries, IPD, Dana, Perfect Circle, will sell any of the 3, while others like TRW and Sealed Power sell only certain components. At first glance, these non-genuine parts look identical, but as you've all just learned, there are a great many details that make the difference. Remember, competitive replacement parts do not meet our specifications. For example, competitors do not roll burnish pin bores. The accuracy, surface finish, and the flatness of the ring grooves of competitive pistons is lacking. In other instances, the critical dimensions are inaccurate. If the height of the piston is too tall, it may strike the valves. Too short a piston will cause incomplete combustion and poor fuel economy because it will not compress the air sufficiently in the cylinder. The oval shape and taper of the piston may also be incorrect, again causing poor performance. A piston which expands too much could seize, while too little expansion would strain the sealing capacity of the rings. Since competition is often simply copying our design, they have to work with looser tolerances. In addition, our dimensions have been developed as a result of lab tests measuring cylinder pressures, temperatures, and loads. It's doubtful if competitors have this information. Sometimes manufacturing shortcuts are employed, like casting in the heat plug rather than bolting it in, or steps are omitted completely. Non-genuine components often result in higher oil consumption and higher blow-by. As blow-by increases, there are some minor power losses and increased oil contamination. Pistons and rings will run hotter, and this causes them to wear faster. Wear on the entire engine will also increase as carbon and other particles that slip around the rings are deposited in the oil. Metallurgically, there's often a great variation in chrome plating thickness on rings, or heat-treated microstructure, such as perlite, a softer phase of iron, rather than martensite, a much harder form which CAT uses. It's small differences like these that make reduced service life and higher operating cost per hour for your customers. Point out to your customers that details do make a difference in engine performance, life, and value to the customer. Keep it CAT.